Okay. Special case of this is when we're dealing with finite sets. Suppose I have just a finite set of outcomes. I put them together in a set, and I'm interested in the probability of that set. So here's our sample space. There's lots of outcomes, but I'm taking a few of these, and I form a set out of them. This is a set consisting of, in this picture, of 3 elements. In general, it consists of k elements. Now, a finite set, I can write it as a union of single element sets. So this set here is the union of this one element set together with this one element set together with that one element set. So the total probability of this set is going to be the sum of the probabilities of the one element sets. Now, probability of a one element set, you need to use the brackets here because probabilities are assigned to sets. But this gets kind of tedious. So here one abuses notation a little bit, and we get rid of those brackets and just write probability of this single individual outcome. In any case, conclusion from this exercise is that the total probability of a finite collection of possible outcomes, the total probability is equal to the sum of the probabilities of individual elements. So these are basically the axioms of probability theory, or, well, they're almost the axioms. There are some subtleties that are involved here. One subtlety is that this axiom here doesn't quite do the job for everything we would like to do, and we're going to come back to this at the end of the lecture. A second subtlety has to do with weird sets. We said that an event is a subset of the sample space, and we assign probabilities to events. Does this mean that we are going to assign probability to every possible subset of the sample space? Ideally, we would wish to do that. Unfortunately, this is not always possible. If you take a sample space such as the square has nice subsets, those that you can describe by cutting it with lines and so on, but it does have some very ugly subsets as well that are impossible to visualize, impossible to imagine, but they do exist. And those very weird sets are such that there's no way to assign probabilities to them in a way that's consistent with the axioms of probability. Okay, so this is a very, very fine point that you can immediately forget for the rest of this class. You will only encounter these sets if you end up doing doctoral work on the theoretical aspects of probability theory. So it's just a mathematical subtlety that some very weird sets do not have probabilities assigned to them, but we're not going to encounter these sets, and they do not show up in any application.